All right, so let's go ahead and get started. Like I said, my name is Michael Kennedy. I work for Develop Mentor as an instructor, and here today we're going to talk about C# 5, which was released, is about to be released in October, I'm guessing, with Visual Studio 2012 and all that stuff. And we're going to also talk a little bit about the task class and APIs that were introduced in .NET 4, because as you'll see, the C# 5 parallelism concepts are built entirely on top of what was introduced in C# 4. And my experience is that not too many people have a lot of experience with that. So we'll spend just a few minutes in the beginning getting into that. So first thing I want to do is actually give you guys a little bit of a poll and just ask, what is your background so that we can aim that right. So let me go ahead and launch this poll here. So if you could just fill out really quickly what your background is. All right, excellent. I see one of you are already using async and await. That's really cool. Some of us are doing a little threading, not too much. Excellent. Some people are just using the older threaded APIs. Very well. Okay. All right, some guys are doing the task stuff. Excellent. So I would say probably 70% of you are either doing system.threading, .thread type parallelism, or none, or a little bit down there. Okay, so here, let me share the results with you guys. So that's how it breaks down. And that's not too surprising to me. The traditional .NET APIs have been around since 2001, 2002, when .NET first came out. There have been several evolutions of new APIs that try to make it a little easier, a little more manageable, sometimes relying a little bit less on using classes, extra threaded classes, and just hooking on to existing classes. For example, if you have like a web client, you wanted to do a download, there's at least 3 ways in which you could do that now, and they've sort of built up over time. They didn't start out that way. Okay, so one thing that we're going to see that's really great about the task classes, and then of course since C# 5 builds on it, that as well, is that these are unifying APIs. They sort of encompass all the functionality that you might have seen in all the older APIs. So the threading, the thread class, the delegate.beginInvoke style, the async result style programming, all those different things, you'll see that we can fold into just this task class, and then we'll build on that with C# 5. Okay, so let's go back to my screen. Perfect. Thanks for doing that. Oh, and I see there's also a question. Let me see what that's about. Older API. Okay, great. Thanks. Go away. Okay, so, oops. Why do we care about threading in the first place? Here's a really interesting graph, and if you look at the date on it, the date is from an article a long time ago, but the graph has actually been updated with up to 2010. So for a long time, we were able to build these applications, and if the application wasn't fast enough, all we had to do was just wait 6 months, a new processor would come out, our machines would be twice as fast, and all of a sudden our application seemed plenty fast, and we just kept on going. And people sort of referred to that as the free lunch. All right, but something really strange happened around 2004, 2005. This dark blue graph here, this is the CPU clock speed, and that was what people sort of thought of as Moore's law, but the real honest Moore's law was about the number of transistors, right? That's the green one. So people thought of, well, Moore's law is doubling the speed of our computers every 18 months or something like that, and at some point it just stopped. They hit a physical wall where you can't go faster, right? If you start to burn up the chips, you have no more space to put things in there together, and basically they change the way in which computers are sort of increasing their processing power, right? So you can see a lot of computers sort of hit this limit, and they even slowed down some. Now, I have a brand new computer, and it has a whole bunch of transistors, but it doesn't have much higher clock speed than the stuff from 2005. But let me see if I can pull up a Process Explorer here for you. The way they're doing that is, of course, by having multiple CPUs, right? So here I have 8 cores on this machine, and they're all, kind of doing stuff. I've got a couple of recordings going and stuff, and screen sharing takes a lot out of it. But if we want to take advantage of this processor, we can't just write single-threaded applications. We need to write parallel applications that will actually leverage all these different cores. Because if I have one app and it's just completely pounding the CPU, the most I'm going to get is 12% usage out of this. And this is just the tip of the iceberg, because if you look at the chips coming out of Intel and AMD going forward, they're going to have many more cores than just 8, right? So if you've got a 128 core machine and you don't do parallel programming, the most you're going to be able to leverage it is less than 1%, even if you're just completely pinning the CPU there. Okay? So basically, around 2004, 2005, we've had to, as developers, start to take multi-threaded programming serious, not just for sort of server-based applications or scenarios where you don't want the UI to be hung up, so you want to do something in the background, but just simply to have our applications leverage the hardware they're running on. Okay, so by the way, if you want to find this article, just Google "the free lunch is over," and that'll do it. Okay, so our agenda for today, we're going to first talk about the task class, which was introduced in C# 4, and that's basically the foundational stuff. We'll see that C# 5 introduces 2 new keywords, async and await, that work together, and they really could have gotten away with a single keyword, but it would make sort of debugging harder, so they make it a little more explicit with this second keyword here. So what we're going to do is we're going to first look at the task class, and then we're going to see how we can build on it. And these async and await keywords are really super simple, but what they're doing behind the scenes is there's a lot of compiler magic, and you need to understand the task stuff pretty well. Okay, so around 2010, we had .NET 4 introduced, and .NET 4 came along with this task class. So the task class is really similar to the thread class that we've known for a long time, since 2001, 2002. And it takes a delegate, and you can say start on it, just like the thread. But there's a whole lot of features added on top of it that make it much nicer than just the thread class. For example, it can return values, you can compose them, you can sort of chain them together, and so on. But in this simple example, it looks kind of like that. So let's just go do a real quick demo here. All right, switch over to Visual Studio, and I want to show you a couple of key points about the thread class. Okay, so here's Visual Studio 2012, but you could just as well do this in Visual Studio 2010. There's no reason you can't. It's just .NET 4 stuff. All right, so the first thing I want to do is just write a sort of a simple parallel program. Imagine that we've got something like a travel website like Expedia, and a request is going to come into our site, to our system, and it's we're going to have a couple of different things we want to do. Somebody's going to say, I'm booking a vacation, so they're going to want to book a hotel, a plane, and a rental car all at the same time. But you can bet that the rental car company doesn't care what the airline does, right? These systems are 100% independent, so we should be able to parallelize them. Book the car and the hotel and the plane all at the same time. So we're going to use the task class to do that. All right. So let's just do a quick bit of coding here. So we'll say book car, and let's suppose this returns an int ID, let's call it car ID equals that, really quick. And then we can do this little trick. We can hit control period in Visual Studio, and it'll actually write the function for us. So let's do that for hotel, hotel ID here. And we'll do the same thing for what's left, the plane. Okay, plane. So we'll let Visual Studio write those 3 functions. Now, as you can imagine, not implemented is probably not what we want to do. We're not really going to call some web services just to keep things simple. We're just going to make the system run a little bit slower just to simulate a web service. But let's do this. Let's say console write line, booking plane, ... In the bottom we can say done with plane. And let's go ahead and also create a static rand, just to simulate some sort of ID or something. So we'll say return rand.next of 100. All right, so there's a sort of a fake web service call, and let's pretend that this takes a little while. So instead of doing real work, I'm just going to say thread.sleep, and for the plane, let's say the plane takes 5,000 milliseconds, 5 seconds. For the hotel, let's say this is going to take 8, and better put the right words here, hotel, and then lastly for the car, let's say that it takes only 3 seconds. Okay, and also let's time this. So we'll create a stopwatch class. We'll say stopwatch. We got to import that namespace. SW equals stopwatch.start new, and the bottom we'll just say something like console write line finished in curly 0 seconds. And we'll just say stopwatch.elapsed milliseconds, turn those into seconds, divide by 1,000. Okay, we're not doing anything with the IDs yet. We'll figure that out in a little bit. Okay, so if I run this, it shouldn't surprise you. There's no threading going on. It just books a car, which takes 5 seconds. It books a hotel, which takes 8 seconds. And we wait. And then finally, it books the plane, which takes 5 seconds. Or 3 seconds. I think the car was 3 seconds. Yep, so the total time it takes, of course, is the sum of all the parts, right? But because the car has nothing to do with the hotel, which has nothing to do with the plane, we should be able to do these all at the same time. So let's convert this to use tasks. So I'll do this here, comment this out, and I'll say this is the serial way. And so when you guys get this code, which of course I will give to you, you can see all the different ways. So we'll see this in a couple of ways here. So instead of doing this, let's actually create some tasks. So I can say task. Now because what the result of this booking a car is an integer, we can actually say we want to create a task of int, and that will store the return value, which will be the car ID. Okay, and you can see that that's coming from system.threading.tasks.task, which is a different namespace than the old one. So we got to import that at the top. All right, we'll call this car task equals, and then kind of like our stopwatch here, there's a factory way to create these that's a little simpler if you want to create and start them at the same time. So I could say task.factory.start new of int and give it the book car, like that. And then you just give it the function to call. We could do the same thing for the hotel. Make sure I get these all fixed for you. Okay, and then let's do one for the plane. Okay, so you guys might be thinking, all right, excellent. We're going to be able to do all these at the same time. We have these 3 separate tasks. They're going to run, and it should take not the sum of the pieces, right? Not 16 seconds, but it should take just the longest one. We only need to wait until the longest one is done. The others should already be done since they're all happening at the same time. But it turns out that there's a feature of the task in that that you'll see here in a second. So let me go ahead and just run it, and you might be surprised how quick we can get this to go. Okay, so in 2 milliseconds, we finished booking the car in the hotel. All right, so what happened? Well, it turns out that these threads that are created here, these all create threads, they come out of the thread pool. And the thread pool threads are what are called background threads, and they don't keep the main process alive. So if the main thread exits, then these background threads are aborted. And you can see that here, that we were booking the car in the hotel, and whoa, those never finished, but we still exited. So the thing with task is you have to wait for them to finish, okay? So there's 2 ways we can wait. We could say task.waitAll, oops, not win any, win all, but wait all. The win all is the new version. We say car task, hotel task, plane task, and just like that, okay? So that's one way to do it, and that's something you'll do a lot of time if you have a void piece. So here you can see now we're waiting for them to finish, and they should finish in order of however short they are, like the shortest one first and the slowest one last. So you can see that they did finish in the same order. Let me see if I can run them in a different order because I wrote them in slowest order. So let's run the hotel first and then the car. You should still see the car finished first. All right, so car is the shortest. It was 3 seconds. The plane was 5 seconds and the hotel was 8 seconds. So, right, they just finished in whichever order they take. Wait. Let's put hotel last, actually. Or, sorry. Put it like this. Yeah, I guess they all just start at the same time. Sorry. It's just random. Oh, there we go. All right. Finally got the plane and the hotel to switch places. But you can see it's taking 8 seconds. And the reason it takes 8 seconds is that's the longest task. Okay? So this is an interesting way to wait for them. We could do this. But we could also do this. We could say console write line, finished booking, car ID, keep writing card, car ID equals curly 0, hotel ID equals curly 1, and plane ID, right? These are like your confirmation numbers or whatever that you would get. And I could just do this. I could say car task dot result. And that's that integer that was returned because we have a task of int. This is sort of the return value here. So we could also say hotel task dot result and plane task dot result. Okay? And what will happen is we're going to run through these, start them off straight away, and then we're going to get and try to write out this line, but the runtime will try to access the value of result, but result is not available. So it's just going to do exactly the same thing as waiting. It's going to wait until the car is done, and then it's going to go and try to access the value of hotel task.result. It's going to wait until that's done, and then same thing for plane. So we don't actually need to wait if we're accessing all the values. Okay, so you can see it didn't just run to the end. It's waiting. We're waiting for the car to be done, then the plane, then the hotel. Right, and then we get these IDs back. And I forgot an equal sign, but you get the point, right? Okay, so that's almost enough foundational stuff on tasks. There's just one more thing. What if I wanted to do something like this? What if I wanted to say, when the hotel is done, I need to go do additional booking? Like I need to, make sure I set some preferences. Like maybe you've set up in my Expedia type of website that you always like a room with a great view. And so we could say, set up something that after the booking is made, we could go back and send something to the hotel. So if we wanted to do that, we could say hotel task dot continue with, and we can chain additional tasks into it. And you'll see that the C#5 compiler does all sorts of magic with this concept of continuing with additional pieces of work. Okay, so let's say task, this can be just a void task here. We'll say hotel follow-up task equals continue with. And what we do is we give it a delegate of some sort. And probably the most natural thing to do is to just give it just a lambda expression. So what I can go down here is I can say what's always passed into continue with is the previous task. So basically hotel task will be passed in. So we'll say task prev goes to, and what are we going to do? Well, we got to do something with it. So we'll say console write line adding view note for booking curly 0, comma, task previous dot ID. Okay. And now we should probably wait. If you have just one task you want to wait on, you can wait this way. So what's going to happen is this is going to run. It's going to take 5 seconds or however many it takes. And then when it's done, it's going to turn around and run this task. We don't have to wait for the hotel task because this one, the second task, won't be finished until both itself and the hotel task are done. Okay, so we can just do this wait here. All right, so let me just run it and you guys should see that working well. And then we'll switch over and talk about C#5. So, all right, we don't see that message that we're setting the hotel, right? Okay, so we done with the hotel, then we added the note for the booking of 1, and you can see Hotel ID is 5. What did I do wrong here? Oh, I said ID. Whoops. Result is what I wanted. So here, I'll run it one more time. All right, so this is probably a good place to stop and ask questions. Here you can see hotel booking 63, hotel ID is 63. So if you have any questions, sorry we only have one-way audio here, but you can throw it into the chat window or the question window. And All keep my eye on the little notifications to see if some of those come up. If they don't, then I'll just move over to C#5. All right, excellent. So we create these tasks. You can either say task equals new task and then start it, or you can say task.factory.start new. I like that. It's a little simpler. It's also a unifying API. There's about 5 different ways before .NET 4 that you can create threads. Every single one of those can be represented by task. And so you have this nice single way of doing things. This is very analogous to what WCF tried to do for all the previous networking APIs. Like used to have message queuing and sockets and web services. Now you can just do all that with WCF. Well, task is like that for all the different ways to do threading. You can have background threads, you can have main threads. Right here we're creating task running, a long running task, which is like equivalent to the thread class from previously. Okay, so excellent. Now we're ready to talk about C#5. So C#5, it turns out, takes a broader perspective of what parallelism is and what asynchronous programming really means. So it still supports creating threads and doing all the stuff that you just saw, but it also goes a little bit farther, okay? So I just want to get your mind in the right perspective here. So I went over to Wikipedia and I looked up, well, what does asynchronous programming, what does asynchrony mean, right? And so they sort of talk about events and actions, and they say asynchronous events are those occurring independently of the main program flow. Asynchronous actions are actions executed in a non-blocking scheme, allowing the main program to keep running. So nowhere in this definition do you see threads. And you're going to see that C#5 actually supports sort of a single threaded type of parallelism. And there's a lot of advantages in GUI-based applications for that. And then also supports sort of creating background threads and using the thread pool and all those kinds of things. Okay, so C#5 and VB both introduce these new keywords, async and await. And what they do is they let us build applications as if they were serial, right? As if they were just single-threaded applications, and then go put a few keywords in a couple of places and then make them multi-threaded, but not change the way that we write our code, because it's really difficult for us to reason about program flow in asynchronous ways. Like when we created that task, and then when the program runs and it runs this book hotel, then it comes back and then it continues with this other delegate, which might call other delegates. It turns out to be very hard to debug, but really, especially mentally, to keep clear what's going on and to write bug-free code. And so what we can do with C#5 is we can write code as if it were just the basic non-multi-threaded code and then turn it into a parallel version using these keywords. Okay? So continuing on with like sort of exploring the different ways we might do threading. The example we just did with Expedia looks like this, right? We have some kind of request comes in and we kick off 3 separate threads on 3 processors. We do them all in parallel and then we wait for them to be done. Right here, we wait. And then we gather up the results and we keep going. So this is a perfectly good example of asynchrony. All right. Now in our world, we actually blocked waiting for the results, but that was a choice our main thread had. It didn't, it's not like the threads actually block the main thread. Okay. But another example might be something like this. Imagine I have 3 large pieces of work. One of them is represented by blue, one is green, and one is red. So if I could take these big pieces of work and break them into small little bits that could be done independently, and I would intersperse them on, say, like the Windows message pump here, and then the message pump would pull them all out and do a little bit of the blue work, do a little bit of the green work, do a little of the red work, and keep going. For each part of it, if those are small enough slices, it would feel like it's continuing to run just fine. Right? Even though there's little blocks where it's kind of locked up, it still would be effectively what we would consider asynchronous. All right? So you'll see that C#5 actually supports both of these. Okay? So what's the trade-off? Well, if we choose the top way, we have a lot more thread safety concerns because we actually have stuff happening on multiple threads at the same time, right? So we've got to be really careful about race conditions. The programming model is more difficult, right? We've got to kick off a bunch of things and then gather up the results. That can be really tricky, and so on. The version on the bottom is simpler. One of the benefits down there is if we're working with, say, UI controls like WPF controls or Windows Forms controls or something like that, or even Metro, by the way, this is all in Metro, Windows 8 as well, then we won't, even though we'll be able to simulate parallelism and keep things running, we won't actually have to worry about doing things like moving the call back onto the main UI thread, because if you've ever tried to access a control from a background thread, that doesn't work so well, right? You get an exception. Okay, but one of the drawbacks of the bottom one is you don't actually take advantage of the 8 processors on my machine, right? You're still just doing single thread stuff, so you're still only at most leveraging 12% of my computational power, all right? So you might choose one over the other based on that. Right, so give me some examples, right, is what you're asking. I'm not sure if everybody can see this, but it says, please talk about some examples, ideal situations when one should be used over the other. So what I would say, and it'll be much clearer after you see this, we're just about to jump into a demo and do this. If you're not doing stuff that's computational, that really is trying to leverage the CPU, I would prefer the bottom stuff if you're doing GUI programming, because it's just simpler. Really what you're trying to do is not block the main UI. You'll find there's a lot of stuff you're waiting on in web and Windows applications, right? You might make a web service call, but you're just waiting on that socket to receive the response. Or you're talking to a database and you're just waiting for the return value from the SQL query and so on. Okay, so those scenarios, we could actually just let the main thread just keep running, okay? Yeah. What is the newest way, either task or async and await? Another question. And how do we access the shared data? Okay, so that's a good question. Let's switch over and I'll show you. The async and await is definitely the newest way. So let's just switch over to Visual Studio. And I have a less simple example here, okay? Let me go to this one here. And this one starts from a little bit of a project that I had before. And I think I realized I was playing with it just a minute ago, and I'm pretty sure I should not have changed it, but I did. So let me just make one quick change here. Sorry about that. One more. Apologize about that. Okay, so let me just run it first, and then we'll come back and talk about what it is. So this is a WPF application. And what it's going to do is it's kind of like a search engine, like a client-side Google or whatever. So what it's going to happen if I type in here, maybe I want to know about the fancy new tablet that Microsoft just released. So I could go do a search about Surface. So let me go and show you what's going to happen when we click on that. So it's using MVVM. Here's the main window view model. We're going to go down here. When we click search, what it's going to do is it's going to go to the entire internet, look at all the URLs there, and it's going to loop through each one of them, download them on demand, do a basic search, basic keyword search for the contents, and then the ones that it matches, it'll show them. All right, so the entire internet, here I can show you guys, is basically like 20 or 30 news-based websites, okay? But the thing is, this method is going to be called when I click the button, and it's not going to return until it's downloaded and processed results from all 30 websites. So let me give this a shot, and you guys will see what happens. So if I click search, you can see that the color is sort of still stuck on what it was for the highlight, and I try to move it, it's not going to move. It's totally locked up. But the program's not broken. It's actually doing the download right now. Eventually we'll see that it'll come back. Oh, there it goes. It must have not found anything. Let's go search for iPad. All right, so it's searching, thinking away. Okay, great. So finally, it's gone and got the results. You know, 1 million iPads were sold last quarter. That's unbelievable. Wired.com is talking about the iPad. We can double click it. It'll like pop open a browser and show us, so presumably someone here, iPad, right? So this is the article it must have found when we went and searched that. Okay. So the app is working. And it turns out that it's not very computationally heavy either, because really all it's doing is waiting on 30 website requests. So this is sort of a really good example where we might go and use the new features of C#5. Okay. So they're deceptively simple. Let me show you how we do this. What we do is we can go to this method, which is just being called directly through the command binding in WPF. Through the MVVM data binding, command binding type stuff. And what we can do, and we can find the part where all the slow stuff is happening, and it's line 82 right there. And we can just go to definition on that. And you can see we're using the web client. And in .NET 4.5, a lot of these classes that might take a while have been updated to have what are called task async methods. So we've had a client, we could say begin, downloads, begin, I guess not on this one. With web requests, you could say begin get response, or you could say get response async. This one you have a download string async, right? But before this, you're supposed to say client dot download string completed, and you have to subscribe to an event, and then that event is fired, and so on. So there's these previous ways in which we could do this in a parallel way, but it turns out to be very difficult to create composable software, right? So if one thing is calling another thing that's asynchronous and it's calling another thing that's asynchronous, it's really hard to make all those pieces fit together well. And it turns out C#5 is much simpler because you write what looks like top to bottom procedural code with no threading, and then you just sprinkle some magic C#5 fairy dust keywords on here, right? So the first part is to switch this from download string to download string task async. Okay, so we're going to switch this to task async, and it's going to return a task of string. Okay, and that's the task that we've seen the whole time. We can go do task stuff with it however you like. Okay, but what we're going to do is we're going to use the new keyword. We're going to say await. Now you can see it's got little squiggly lines and stuff, and says you can't do this. This is just a convention that they put into C#5. It technically could have been done without it, but they said if you're going to use this word, you need to sort of declare your method as being an asynchronous call. So you have to say async up here, and then you can see that await turns blue, and we can now do this. Now there's something really interesting here. If I hover over this, you see tasks of string is what comes back. But on the left side, after we process and await, what we get is var is actually a string. So even though download a string task async returns a task of string, the await keyword says you don't actually care about task. That's the mechanism by which we make this work, but you don't care about task. You just want the result. You're waiting for the result and give me the result. So what you get out the other side is a result, a string in this case. Okay. Then the other thing that's weird is this is a string. Let me go ahead and write it as string now so it's really clear. We're returning a string here, but it says that you have to return a task out of your async method. So what this really needs to be is a task of string. But where it gets interesting is we say return string, and yet the return type is task of string, and there's no compiler warnings, right? If I press build, it's totally happy. Well, okay, it's not totally happy because the methods that we're using this one are broken, but you can see there's no errors in the downloader class file. It's only in the view model. Okay, so this is basically C#5. What you do is you work with methods that return task. You typically task of results. You could await a void task, but you would just have no return value. But you await the result, you get the actual result as the direct value, and then off you go. So let me run it first, and then I'll come back and dissect what's happening here for you. But there's this other problem, because back up here where we were calling this, it said this was expecting to return a string here, right? That's how it was working before, but it no longer returns a string. So what we need to do is say, okay, fine, well, I actually wanted the value out of that. So you kind of got to walk your way up the stack and say, I want to use await here. And so in order to use await, I got to use async, just like that. And then it should be good to go. All right, now it'll compile. And something really interesting is going to happen. So it's going to run down here. When I click this button, it's going to run just normal main thread until it hits this await. And then it's going to say, all right, well, this is not done. I've got this task back. I'm waiting for the task to complete, but it's not done. So it's going to release the main UI thread to keep working. And it's going to convert this second half into a continue with. And when the task is finished, it's going to put a message on the message pump. It'll pull out and it'll continue processing this bit. And it gets a little more complicated because we're in a loop. So you can kind of think maybe, well, it'll just run down within the loop. Then it'll turn it into another continue with and another continue with and so on. And we'll look at this in disassembly in a minute, but let's just run it and see it working. Okay, so we searched for iPad before. Run, see it's moving, results are coming in, we've hit CNN, now we hit CNET, and now we got breaking news from that place, which is what, MSNBC or something? Okay, look at that, we've done almost no work. We've just put async and await, two different locations, and down here in the downloader, we've used converted from the download string to download string task async. And so what the C# compiler does is it basically writes the code that we wrote in the first example we saw in the console application. It says, okay, well, we need to break this into a bunch of tasks, and the stuff that happens after the task is done is a continue with, but it adds on some additional magic to actually keep this happening on the right thread. Okay, so what's really interesting here is when I go and search for, like, let's search for truck or something. Okay, so when I go do this search, I'm still able to update the UI from the background, from these sort of asynchronous pieces of my application. I don't have to, check and see is it a background thread and cycle it back over to the main thread. And so that saves us tons and tons of work. We could actually go and ask it. We could say something like, let's say, debug.writeLine, current thread ID. We could say thread, sometimes IntelliSense gets too helpful, current thread manage thread ID. Okay, let's say that here. I can say that here, and let's also say it right in the constructor where we know it's on the UI thread. Okay, which is right. Let's say right here. Okay, so if I run this in debugger, it should always have the same ID. There's no extra threads. In other words, the kind of work we're doing is this bottom version of asynchronous programming, not the top version. There's ways to do the top version with async and await, but what we've done so far is not it. Okay? Oh. And you cannot update it while it's running. That makes perfect sense. Okay. So go and run it. And let me run it in the debugger so you see the debug output. And let's search for iPad again. And down here in the output window, you could see right in the beginning, current thread is 9. Did I ever press go? I guess not. There we go. Now it's going. So see all the stuff before we download the content, after we download content, it's all the same thread. We're not doing multi-threaded programming, we're doing asynchronous programming, which is a broader concept, right? Okay. So let me undo those guys. We don't want that messing up our code here. And excellent. Okay, so let me show you one more thing I'd like to do. What I would like to do is I would like to look at this method, update stats. So what I want to do is every so often, I would like to go and ask the search system, which is doing the download. How many downloads you have pending? What thing are you currently processing? So if you go and look at here, it says idle at the bottom. And you may have noticed it always says idle. Even while it's downloading, it says idle. And so there's this update stats piece that's supposed to update that. Okay, so let me just go and call it at the beginning, right in the constructor. Right when we create our application, we'll get started and do this, okay? But notice, while true. When do you think that's going to return? Never, right? It's an infinite loop. So if I go F5 and I run this, well, it's starting our app, and our app is running. You can see Web Searcher down here is actually running, but it's not showing the window. And the reason it's not showing the window is it's never even returned from the constructor. If we hit pause, then go up the call stack one bit, right here you can see it's still stuck in update stats. Okay, so that's not surprising. You know, you've all known that if you write a while true loop and you never break out of it, well, you're kind of stuck there. But let's do something really interesting here. Let's say we don't want to do this too often. So we can say this. We can say task.delay. We can say we want a task that will complete in 200 milliseconds. Now that seems completely useless, but we can put a wait in front of it. And of course, this means we have an async here. If we put a wait in front of it, what it does is it's going to say, okay, program, run to here, and then release program control for 200 milliseconds, and then run this little bit of code, and then release program control for 200 milliseconds, and so on. Now, in the constructor, I didn't update how I'm calling this. I'm not doing anything different. I just call update stats. But you're going to see something pretty amazing here. First of all, we're still calling it, and our UI is now working. If I say iPad and I search, watch the bottom, the status bar. 23 pending, we're searching Fox News, MSNBC. So we've essentially kicked off like a background task that every 200 milliseconds is checking the status of the search engine and updating it. And yet, it's doing it on the UI thread. It's created this mechanism by which every 200 milliseconds, the Windows message pump goes and continues working, right? So that's really, really interesting. And if you look at the CPU usage, it's still super, super low. This is, that adds almost no overhead because the amount of time that takes to run versus 200 milliseconds is like, 0.000. It's super, super small. Okay. So that's a really interesting use. We have maybe 14 minutes left. Let me look at the slides for a minute and sort of catch us up there, and then I'll show you one more way to sort of go down this more towards true parallelism. We won't actually go and do too much of this, but one thing that you notice is if I go and run this over here, in the output window, it shows us what it's searching. Let's just do a clear. Okay, and so if I go search for iPad up here, or if I could spell it right, you'd see it's first doing CNN, then Fox News, then MSNBC, then NPR, then Boston News, then Dallas News. It's doing them in order, right? There's no actual parallelism. Like we saw with our Expedia example, that really had parallelism. Stuff happened faster. This is no faster than before. It just lets my UI update and my screen get moved around. And if I wiggle it, apparently I'll minimize Visual Studio. There we go. Okay, so the last thing in this example to do is to actually make it do stuff in parallel. Okay? So it turns out that that's not hard at all. We just have to rewrite one of our methods here. So the thing is, this method is asynchronous, but what it does is it runs down and it waits for one thing to finish, and then it processes it, and then it starts another one and waits for it to finish, and then processes it, starts another one, waits for it to finish and process it. Okay, what we need to do is start them all, and then when any of them are done, then we want to actually go and process them. All right, so what we have to do is write 2 for loops. Okay, and this turns out to be a while loop at the bottom. Let me just say false for a minute. Okay, actually true just so it doesn't get grayed out by ReSharper. Okay. Now there's a few things we got to patch up here, but let's do this. Let's create a list of tasks. Whoops, got to import. This IntelliSense is too much. List of task. Downloads equals new list. So what we're going to do is, instead of awaiting on these right away, we're going to do this. We're going to say downloads dot add. Now first we'd start out writing something like this, right? Just gather up all the tasks, and then later on we're going to wait on them. But it turns out we have this problem because we actually need two pieces of information to process the result. We need what the URL is and what the content at the URL is so we can search it, right? We need to know the URL, so if you double click it, we can take you there, and we need to know the content so we can search it. So what we have to do is we have to basically create a simple object that just stores both the URL and its content. So at the bottom, I've got this little super simple method here. This thing we called download result. Okay, and all it does is it just calls downloader.download HTML, but it also creates this download result and stashes it together. Okay, so we're just going to call this. We're going to create a list of these things. It's going to look kind of ugly in the delegate style here, or in the generics, but that's okay. So what we need is a list of task of download result, right? This is a good time when maybe one might want to say var and forget how ugly it looks. And then instead of doing this, we're going to just say download URL. Okay. Now we're not really doing anything complicated there. We're just creating an object which holds both the URL and the HTML. So the next thing to do here is we're going to create a task of download result. Result. And what we're going to do is we're going to go to all of our downloads and we're going to ask it a question. We can say task.when any. Okay, when any of these tasks are done, we're going to store them in here. And maybe result is already used, so let's call it finished task. Okay. So when any of these are done, we're going to grab that download result. And we also need to go to downloads and say remove finished task. All right. And this returns a task of a task, which is kind of crazy. So we need to just do an await. So we're going to await. Whenever the first one's done, we're going to get the result back, which is one of these tasks. Okay. And let's actually put this down here. And the question we're going to ask for our loop is we're going to say while this count is greater than 0. Then we'll say finish task.result.url. And down here at the bottom, we're going to say, instead of HTML, we're going to say .data. Data is the HTML. Okay. So instead of awaiting each of them, we're going to start all of them. And then as they finish, that's what when any does. We could say when all, and that would just block till they're all done. But we want to process them as they get done. So we're going to say when any of them are done, give me the first one that is done. We'll take it out of our pending list, process it, search it, and then wait again for more to come. Okay? So if we run this now, you should see this go much faster. All right, so first let me clear out this window. At minimum, you should see them go in parallel here. Okay, so let's go search for iPad again. Run. See them all downloaded in parallel, and they're all finished. Okay, so search again. I can move around. Now they're all finished. Okay, pretty cool. I see there's a question. If two finish at the same time, would that logic skip the second one? Great question. No, it wouldn't. It wouldn't skip it. Basically, this thing, if two of them were done, it would just go through the list and return the first one that's done. And then it would immediately, basically the second time through that loop, it wouldn't wait. It would immediately return the second one rather than the first one. Because that second time there's only one that is finished. Okay? So yeah, no, that would be fine. Now, you might have noticed, it's probably really difficult over GoToMeeting, but if I search, and as I move around, it's sort of stuck, right? It's not quite as smooth of an experience. And the reason is, this second part now is starting to dominate the processing because we're downloading so much so fast. The search engine actually takes a little bit of time to go through all the HTML. There's a fair amount of string processing to get through all those home pages, okay? And so this part, which is not asynchronous, is starting to really bog down the system. So what we could do is write a method that does this stuff in serial, or yeah, write one that does it in serial, and then use convert them to tasks. Okay, so the way we would create something like that actually runs on a background thread is you would say task.run. All right, task.run is kind of like the task that we had before, but it actually creates one. Here you can see right in the description, queues specific work to run on the thread pool and returns a task for that. Okay, so that lets us get back and do some of this true computational processing. All right, I don't think we have enough time to really go into that. It's kind of a little bit tricky. It's not super hard or anything, but let me just make a note then. Convert these calls to task.run. Then you get, maybe we would want to say await task.run. Then you get full parallelism. Okay. All right, so I think that does it for our demo. We started out with just a purely straight single-threaded application. You saw that we made the UI responsive simply by adding await and converting async and await in two simple locations, and then converting from download string to download string task async over in our downloader piece here. Right? Just add task async and then await and async. But that didn't actually add more parallelism to it because we were awaiting each result, still sort of doing them in order. So we had to actually change our logic ever so slightly to these two loops. First start all the operations and then pull them out as they're done with task when any to actually get more parallelism out of the system. Okay, so hopefully you guys got a good idea of the C# stuff that's happening. The last thing I want to do, let me go over here and go to the folder here. I want to disassemble this thing and see how it looks. So if we go over here, when we had this as just the simple version, let me throw in something I'll just call serial and just make it a string, just so we can see it in the disassembly, so we know kind of what we started with. Await. There. Okay, so let's look at this in Reflector, which I thought I had open, but I guess not. So hold on a second. Down here. Here we go. Yes, and let me go ahead and close it so it'll actually build. Okay, so let's go and throw this into Reflector here. That it would be the web searcher.exe. I think here. Let's close that up. Okay. Oh, it's .NET 4. Oh, it does not support .NET 4.5? Interesting. Well, maybe I won't be able to show it to you, but I can still at least tell you what's in there. So if you look at what's happening inside here, if we disassemble this version, right, this download HTML serial, it would look very, very similar to what you would expect. But if you throw this version into Reflector, which I do have two versions. Let me see. Maybe it's the second one down here. Nope, same problem. Okay, well, what you would see is basically it creates a state machine. Okay, and it looks absolutely nothing like what you see written here. There's a whole bunch of classes that are created, and this code has a bunch of go-tos, believe it or not, in it. It looks really quite unusual. But basically, if you were to work out what it's doing, it says run this code down to here till you see the first await on the main thread, the calling thread. Convert this to a task. This download task a string, really it is a task already, so there's not much to do to it. But then convert this last bit here to actually a task.continue with. Okay, so that's why it's super important that you guys get that task stuff down, the continue with stuff down, because really that's what the compiler is doing for you. All right, but the real benefit is we don't have to write inside out code that sort of creates a bunch of delegates and passes them off and then waits for them to finish. That turns out to be really hard to do, right? You just write regular serial code and then you let the compiler turn it inside out so that it can be asynchronous. Okay? So questions, comments? I think I'll just leave it at that. All right, so like I said, if you go to develop.com and you go to webcasts, then you should be able to find the asynchronous programming in .NET 4.5 down here. All right, and we should have the downloads and so on. Also on Twitter, if you follow me on the Twitter, go back to the beginning, at mkennedy, then I'll send something out today where I have links at least to the downloads. If we have the video ready, I'll point at that as well. But that might take a day or two to get ready. All right, so unless there's other questions, just wanted to say thank you for coming, and I really appreciated the time to talk about threading with you.